If your embeddings kind of match but miss the exact passage, late interaction is the fix. We'll build a colBERT retriever that actually finds the right snippet. You have a symptom. Your semantic search often returns a related paragraph, but not the exact line you need. By the end of this video, you will understand how colBERT late interaction boosts precision, and how to wire up a tiny PyTorch example to see it live. You will be able to index short passages, inspect why a passage scored well, and tune the candidate depth for speed versus recall. I'm Professor Pi, teaching search and IR from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. colBERT with late interaction is a middle ground between full dense retrieval and token-level matching. People use it when a single dense vector loses fine-grained term alignments and exact phrases matter. Success looks like returning the exact snippet that answers a query, not just a related paragraph. For many document collections, this improves hit rates for factual questions and snippet retrieval. The intuitive idea is to encode query tokens and passage tokens separately. Keep token-level vectors and score by matching each query token to its best passage token. That per-term best match then sums into a final score. It preserves token detail while staying fast enough by first pruning candidates with an approximate index. Strengths are precise phrase sensitivity and explainability. A downside is extra compute during the late interaction step compared to a single vector compare. We will build a toy index of 3 short passages, run a query with MaxSim scoring to see the top passage, use explain mode to inspect per-term contributions, and then test how changing the candidate pool size affects the top hit. The examples use the official colbert-ai components and a local PyTorch checkpoint named colbert v2.0, so you can reproduce the behavior locally without large corpora. Now we create the tiny index. This snippet builds a tiny colBERT index from 3 short passages. We import the indexer from the official colbert-ai library and define the list docs as our miniature collection. The indexer call loads the local PyTorch checkpoint colbert v2.0 and encodes passages with late interaction embeddings. The index method materializes a new index named toy using the in-memory collection, so no external files are needed. Keeping passages short reduces tokenization and encoding cost, which makes the indexing step quick. The printed value confirms the index is created and ready for search. Next, we will run a basic search against the toy index. This snippet queries the toy colBERT index and returns the top passage. We construct a searcher from colbert-ai, pointing at the toy index created earlier. The variable q holds our query, and the search method retrieves candidates with colBERT's MaxSim late interaction scoring. Asking for k equals 3 returns the top 3 passages ranked by summed per-term maxima. Increasing k provides more candidates and slightly increases latency, while decreasing it does the opposite. The printed top text shows the highest scoring passage for this query. Now enable explain mode to see why a passage won. This snippet uses colBERT's explain mode to expose MaxSim contributions. We rebuild a searcher on the toy index and issue the same query with explain equal true to request per-term evidence. The object E carries explanations where explanations.maxim holds the maximum similarity for each query token against the passage tokens. We sum these maxima into MS to match the overall late interaction score used for ranking. Setting explain equal true increases compute and memory overhead, so disable it for production. The printed MaxSim sum shows the total MaxSim score that drove the top 1 decision. Next, we compare shallow and deep candidate pools to see stability. This snippet tunes the candidate depth FAISS depth to trade speed and recall. Using the colbert-ai searcher, we run 2 searches for the same query, but change the ANN candidate pool size. The variable A uses a shallow depth, and B uses a deeper depth before exact late interaction scoring is applied. We compare the top passage identifiers to test whether increasing the candidate set changes the winner. Larger face depth improves recall but increases latency. Smaller values do the opposite. The printed Boolean indicates whether top 1 is stable under this depth change. Finally, we compute a tiny accuracy at 1 for 2 queries. This snippet runs 2 queries and computes a tiny ACK at 1 for our baseline. We create queues with 2 intents that should map cleanly to different passages in the toy index. Using the colbert-ai searcher, we take the top 1 text for each query and compare against a gold mapping stored in gold. The expression computing ACC divides matched predictions by the number of queries to yield accuracy at rank 1. You can raise K and evaluate recall at K if you want a more forgiving metric. The printed ACC1 summarizes how often ColBERT's top passage matches the gold label. To map this toy run to a real project, think of the 3 passages as stand-ins for many short documents, like FAQ entries or paragraph-level chunks from articles. Swap the in-memory collection for a larger passage store. Add an ANN index for the initial candidate stage, and keep the late interaction scoring and explain mode for critical queries where precision matters. Recap! ColBERT late interaction keeps token vectors and scores by per-term best matches. Use it when you need exact snippet retrieval and precise term alignment. One caveat is extra compute at the late interaction step and higher memory for token vectors. Next step. Try tuning the candidate pool size to balance latency and recall. For example, increase face depth and measure top 1 stability and timing. If short, practical IR helps your projects, subscribe and watch the IR videos.